So this is Chapter 11, Vibration and Weight for Mechanics and Motion class. And so for today we have in terms of what would be simple harmonic motion. So if you think in terms of a block on a spring, and so we have this kind of a setup. So we have our spring, and then we have a block on that spring, and if we pull on it, it will go and oscillate back and forth. And the force needed to cause this to happen will be given by Hooke's law. So F is the force, which will be in newtons. K is the spring constant, which will be in terms of newtons per meter. And X is the displacement, which will be in meters. So F here again is the force, which is in newtons. K is the spring constant, which will be in terms of newtons per meter. And then X is the displacement, and that will be in meters. And so we get this simple harmonic motion, and this thing will rock back and forth, and this motion will be periodic. So we have in terms of our spring. And so in terms of the spring, we can look in terms of how far I can pull it without disrupting my spring. And so we get to where we have the amplitude, which will be the maximum displacement. So we have in terms of the amplitude, which will be the maximum displacement. And then we can look in terms of the period of all this, and the period is then the time frame to complete one cycle. And then we look in terms of the frequency, which is the number of cycles per second. And so we've seen before, we have that period and frequency are reciprocals of each other. And so we get that the frequency is going to be 1 over the period. And again, the notation used is that T is used in terms of the period. Right? And the units on frequency will be in terms of hertz. And then we get that the period will be 1 over the frequency, and the units on this will be in terms of seconds for our units. So we look again in terms of our system here, rocking back and forth. We can find out in terms of this frequency, and we can find out in terms of period of the system. So, for example, then, in terms of how all this works, we'll go through a problem. And so, for this one, have again in terms of a spring going back and forth. And so we have, for example, so when a 200 kilogram block is placed on a spring, it compresses 3 centimeters. And then we want to know what is the spring constant. So what is the K value for the spring? And we also want to know how far does it compress when a 300 kilogram block is placed. So when a 300 kilogram block is placed on the spring. So we have our question, and we want to do this, and so basically it's 2 parts. First part is to find the K value, and then once we know the K value, we can figure out how far it gets displaced when I change the mass on this. And so again, we had from before that the force is equal to K over X, which means I can quickly take that equation and solve it for K. Okay. Sorry, actually I have this wrong. That the force is actually given by K times X, And so I can solve that for K, and so we get that K is going to be the force divided by X, and the force acting on my spring is actually going to be due to the weight of my block. And so the weight is going to be 200 times 9.8 divided by X, which was 3 centimeters. And that number has to be converted into meters, and so this will be 0.03 meters. And so the K value for my spring ends up being 6,500 newtons per meter. So that's the K. And so basically K is a value that basically tells you how stiff that spring is. And so basically this is sort of a spring that you think in terms of for your car. Right? And so now that we know the K value, we can figure out how much the spring will be compressed, given that now the mass is 300 kilograms. So again, we got F equals Kx, and so now X will be the force divided by the K value. And so here the force will be due to the weight of the new block, so 300 times 9.8 divided by 65,000 newton meters. And so we find out here that the spring will now move 0.045 meters. So we can figure out here in terms of our K value for our spring, we can then figure out how much it depresses or expands given the new block. Okay. So then in terms of our system oscillating back and forth, we can look in terms of the energy in the system. So we talked before in terms of energy, in terms of kinetic energy, and in terms of potential energy. So we can look in terms of the energy in a simple harmonic oscillator. And that energy will be made out of 2 parts. So the potential energy part in our system will be given by 1/2 kx squared. So that's how much potential energy is stored in our spring. And then we get the kinetic energy part of it, which is what we have seen before, which will be 1/2 mv squared. Right? And so the total energy in our system then will be given by these 2 things put together. So we get the total energy in our simple harmonic oscillator. So again, if you think in terms of my spring on a block. Okay. And we can look at this spring in terms of being in different positions on here. Okay. So we could have it when it's at its normal resting position. So x is 0. We could also have where we stretch it out and we get to the positive x, which will be equal to the amplitude of this. And then we can get to when it gets to its compressed position. And this would be negative x. And this would also be the amplitude. Right? And so we can look what happens in terms of our system at these various places. Okay? So when I'm at here, when x is equal to 0, well, when x is equal to 0, that would mean that there is no potential energy in my system, and so the energy here would just be due to the movement of my block. Right? So basically we got that we pull the block, it starts oscillating back and forth, and when it gets here, the only energy it has will be due to its kinetic energy. Right? So when we get to where x is equal to a, right? Well, when x is equal to a, we're out here at the very end, and so we got that the spring is going this way. It gets here, and for a brief moment, you have that the velocity will go to 0. So velocity will go to 0, and so now the energy will just be equal to k times the amplitude squared. Right? And then the same thing would be true when my block is at this point. When we're at negative x, then we also get the same thing. Right? But then we get where the block is somewhere in between, and so now let's look what happens if instead of being at the 0 mark, which was here, the amplitude mark, which was here, we now have that my block is now somewhere in between those two marks. Right? And so when it's at some point in between, the energy now will be due in regards to this entire equation. Right? Right? So when my block is somewhere in between, it has both potential energy and it also has kinetic energy in it. So we can look in terms of our system and what happens in our simple harmonic oscillator as it goes back and forth. Right? Well, in terms of this motion, and if I were to graph it out and see what's happening here as it goes back and forth, we would basically get a sine curve. It's a sinusoidal motion. And this would also be an example of a simple harmonic oscillator. Just goes back and forth, over and over and over. Yeah. In terms of that, we can look in terms of the period of this and what's called the sinusoidal nature of a simple harmonic oscillator. So SHM is a notation for that. So in terms of this, we look in terms of the velocity v over v max will equal the square root of a squared minus x squared divided by a. So in this, a is the amplitude, x is the displacement at any given time. And so we can solve this, and so v is going to equal v max times the square root of a squared minus x squared, all divided by a. Okay? And so we got that V max will occur when the potential energy is zero. Because you think about my spring going back and forth, is that as it's going out towards the amplitude, the spring is going to be slowing down the block. But when it gets to the normal resting point, that is when the block will have its maximum speed. So we look in terms of V max, and so V max can also be written in terms of 2 pi times A over T. So I think in terms of a normal sine wave, the time frame for it to go through a cycle is given by 2 pi. And so this is also the same thing as saying 2 pi A times the frequency. So after all, dividing by T is the same thing as saying frequency. And so the period then will be given by 2 pi times the amplitude divided by V max. And then in terms of this block in my system on a spring, we can also rewrite this that the period will be given by 2 pi square root the mass of the block, okay, divided by K. And so the frequency then, which is just reciprocal, is 1 over 2 pi. And this would be the square root of K over M. So we can look at terms of finding my system here. We can look at terms of finding the period. We can find the frequency. We can find the velocity of the block by going through this. Okay. So this is in terms of a sinusoidal motion of what's going on with my system. And so if you think back in terms of what a sine wave is, and so we look in terms of my system here. So again, in terms of this block going back and forth, goes out to a maximum amplitude of A, which is also the same thing this way, and this is the resting point. Right? So basically, if I think of a scroll of paper going behind this, as this thing is moving, and so let's say it goes out this way first, and then it comes back this way. So if I look what's happening here, and sort of graph what's going on as this is moving, it'll start here at 0, it'll go out to a maximum point, it'll then come back down to 0, it'll then go in the negative direction, reaches the maximum point, and then comes back. And it'll keep on doing this over and over and over, and then again is our picture of a sine wave. So in terms of mapping where the object is, we can look at this in terms of our trig functions. And so we can look at this as being that x is going to be given by a sine omega times t. And so we've seen this before, and that is in terms of the angular velocity. Okay. And we can also say this is the a sine 2 pi t over t. Right? And so t is the time frame. Again, big T is the period, and a is the amplitude of my wave. And so this is when we use this equation when t is equal to 0 and x is equal to 0. So like here, my block was starting at 0, I then started out that way, and I can get a sine wave. We can also look at this in terms of the analogous cosine curve. Okay. And equations are basically the same. And so we look in terms of this, that x is equal to a cosine omega t. And then omega is equal to a cosine omega t, and then omega is equal to 2 pi times f, and so we get x is equal to a cosine 2 pi f times t, which is also then equal to a cosine 2 pi little t over big T. And so we get the same equations whether we look at this in terms of a cosine curve or in terms of a sine curve. And so this will give us mapping the position of my object. Given we know the amplitude, we know the period, we can figure out where this block will be at any given time. So if you think in terms of something that goes back and forth, we can look in terms of a pendulum. So if you think in terms of like a grandfather clock, and you have that pendulum that goes back and forth and back and forth. So in terms of the simple pendulum then, we get this. We get the simple pendulum. So if you think in terms of this, we have our string, we have the bob on the spring, and this thing will go back and forth like that. So it ends up that the period of this, the period for this to do this is going to be given by 2 pi square root of the mass of the bob that we have divided by mg over L. So m here is going to be the mass of this will be m, and that we mass. L is going to be the length of my string. And so if you look at this, you can notice that the m's occur both top and bottom, and therefore the m's will go away. And so this is not dependent upon the mass of that. And so we end up that the period is going to be 2 pi, and this will be L over G. So we get the period, and we could also then look in terms of the frequency. And again, frequency and periods are reciprocals of each other, and so the frequency here will be 1 over 2 pi square root of G over L. And so we get the frequency of our system. Well, we can use a pendulum to figure out the value of G. And so the first lab we did, we found G by doing the ball drop, and we will also do a lab where we find the value of G using a pendulum. Right? And so we have in terms of a question dealing with this and making use of this formula and finding our value of F. Right? And so we can find our value for the gravity. And so let's put the question up here. So we get using a pendulum, right? So using a pendulum, an astronaut wants to determine the value of G on a planet. And so he has that the length of the pendulum is 36 centimeters. Right? And it has a frequency of 0.75 occurs. Okay? So we're going to use this equation, and we're going to take that equation, and we're going to solve this for g. And then from that, we can get what the value of g is on this particular planet. So if I take this equation, and we solve it for g, first thing we'll do is multiply by the 2 pi. So we get 2 pi f equals the square root of g over L. And then the opposite of square root is to square, so I square both sides. So we get 2 pi f squared equals g over L. And then the opposite of dividing is to multiply, and so we get 2 pi f squared times L will give me g. And so now we can take our numbers, we can plug those in, so we get 2 pi, frequency was 0.75, and that will be squared. The length was 36 centimeters, which does need to be converted into meters, and so this will be 0.36. And we plug those all in, and we find out that on this particular planet, that the value of g will be 7.99 meters per second squared. So basically 8 meters per second squared in terms of this. Okay. So we used our pendulum, and we got the value of g on this particular planet. Let me get in terms of this wave motion and this back and forth. We look in terms of the resonance for our system. So in terms of resonance then, we look in terms of the natural occurring frequency for a spring. And so we get F naught, the naturally occurring frequency, would be 1 over 2 pi square root of k over n. Okay. And so you get where resonance occurs. Resonance occurs when the driving force matches a naturally occurring frequency of the medium. Which leads to an increase in the amplitude. Okay? So you think in terms of examples of that, you think in terms of the opera singer hits the right note and basically matches a naturally occurring frequency of a crystal glass and being able to break a glass with their voice. You also think in terms of examples around here, you think in terms of Galloping Gertie and the first Common Narrows Bridge, and that it went in resonance with the winds on a particular day, and that vibration basically caused the collapse of that bridge. So, in terms of wave motion, we again look in terms of our representation of a wave being that nice sine curve. So in terms of wave motion, again, if I look in terms of my sine wave and how that works, we got here's my baseline. And so this would then be the amplitude, is from here to here. The wavelength is the distance from basically crest to crest, or trough to trough. Right? So that distance would be the same at that distance. This distance here, which is the amplitude, would be the same at that distance over there. And so the velocity of a wave is given by the wavelength times the frequency. And if I think in terms of this being a wire or a string, we can also find out that the velocity is given by the square root of the tension in the wire, F sub t, divided by N over L. And so in terms of this equation, you get Ft is going to be the tension in the cord, N is going to be the mass of the cord, or the wire, and then L is going to be the length of the cord. So, given that we have a wire, everything in terms of piano wire, guitar string, whatever, we can find out what the velocity will be given that information. And so we're going to make use of this equation and go through a problem and solve it for what would be the velocity. And so we'll leave that equation there and get rid of some of this. And so we look in terms of this problem. You have a wave with a wavelength of 0.25 meters. It is traveling down a 400 meter long wire with a mass of 18 kilograms. And if the tension in F sub t is given to be 1,500 newtons. And I want to know what is the velocity and I want to know what is the frequency. And so I want to find these two things out given this problem. So we can find the velocity by using this equation. It'll be the square root of that. And so we can plug into our problem, our stuff. And so we get that the velocity will be the square root of my force, which is 1,500, divided by the mass, which was in kilograms, which is the right units. Our stuff. And so we get that the velocity will be the square root of my force, which is 1,500, divided by the mass, which was in kilograms, which is the right units, divided by the length, which needs to be in meters. That number is in the correct units. And so we plug that in, and we get that the velocity here will be 182.6 meters per second. We can also find the frequency because we had that the velocity is given by the wavelength times the frequency. And so the frequency then is going to be the velocity divided by the wavelength. And so we have 182.6 divided by the wavelength, which we said was 0.25. And so we get that this number will be 730, and the units on that will be in terms of hertz. So we have that for this wire. We got that how fast it's going to be traveling under that tension and the frequency of this particular point. Well, in terms of waves and how waves move, there are two types of wave motion. And those two types are transverse and longitudinal. So in terms of those two types of motion, first type is a transverse wave. And so here you have that wave motion and wave direction are perpendicular to each other. First type. And then the second type of wave is a longitudinal wave. And in this one you have the wave motion and wave direction are parallel to each other. So those are the two types of waves that we can have in terms of their motion. So in terms of waves, and other type of waves motion we can talk about in terms of a standing wave. So a standing wave, we have this going on. So in terms of my standing wave now, we have that if you vibrate a cord, so if you vibrate a cord or a wire, at just the right frequency, so the two traveling waves traveling wells will interfere in such a way that a large amplitude standing wave will occur. And then in terms of this standing wave, we can look in terms of two distinct points on it. And so you get that the points of destructive interference, so basically where the two waves cancel out, so basically where the waves cancel each other, those are called nodes. Okay. And then you get that the points of constructive interference so basically where they reinforce each other. Where the waves reinforce each other are called antinodes. We have nodes and antinodes. Are called, sorry, let's make a correction here. There should be nodes and nodes. There we go. So we get nodes and antinodes. So if I look in terms of a standing wave and a representation of that, we can get in terms of this drawing. So I can have a wave. So if I look in terms of the fundamental frequency, I have two anchor points here. We have my wave goes like this, and then we get the counterpart of this wave going like this. And then we got that this thing is vibrating back and forth, and we have in terms of the nodes and the antinode. So this would be the node, and then this is the antinode. Okay. I go in terms of going up, in terms of this, we can look in terms of now something like this. And so we have now again, we have that now we have in terms of three nodes. And then there are two antinodes. So we have N, this is N, this is N, and then we have A, and we have A. Okay. So we get the first, second, third, we keep generating these types of diagrams as we work our way up. Okay. So in regards to this stuff, that we can look in terms of that the length L, so the length of the wire, is going to be given by N times the wavelength of N divided by 2, where N has to be an integer. So N has to equal 1, 2, 3, so on and so on. And so the wavelength is going to be given by 2L over N. So my fundamental frequency here, and lambda 1, is then going to be given by 2 times L over 1, which means that this will just be twice the length of my wire. The frequency, then, F sub n, is going to be given by V over lambda sub n, which would also then be in terms of this. We can also rewrite this in terms of NV over 2L, and so this will be N times the fundamental frequency. So once we know the first frequency, we can really get the second, third, fourth, and so on just by multiplying by whatever we are looking for. So in terms of the fundamental frequency, F1, we get that that will be V over my first wavelength, which will be V over 2L. So that in terms of how this works, we look in terms of a problem. And so we have something that looks like this. What will be the wavelength? Of the third harmonic given a wire and point is 65 centimeters long. So we can figure out my wavelength here, given this. Right? And so we have, and in terms of this equation, that the wavelength is given by 2L over N. And so my wavelength of my third harmonic is going to be given by 2 times 0.65. Again, we need to convert that into meters, divided by 0.3. And so we end up that this will be 0.43 meters. Okay. So we're able to go, we could do this in terms of whatever harmonic we want. We could figure out the value of this. Okay. Well, we can also look in terms of, if you think in terms of piano and how that works. So we can look in terms of a question dealing with a piano string. And so one last example of this. So we have a piano string which is 1.20 meters long, has a mass of 10 grams, and we want to know how much tension do we need to put on the wire. How much tension must be on the wire if we want it to have a frequency, fundamental frequency, of 140 hertz. So we can find that out. So we got that V is given by the square root of Ft over M over L. And so in this case, we actually want to solve this equation for Ft. Okay? And so again, if I solve this equation for Ft, the opposite of square rooting is to square both sides, so we get it V squared is going to equal Ft divided by M over L. Okay? And again, we want to solve for Ft, and so I need to bring this over, and so I do that by multiplying, and so we get that Ft, tension in the wire, is going to be given by V squared times M divided by L. Right? Well, so that's that equation, but we still, in order to do this, we need to know what V is, and so we can find V by knowing that V is going to be given by the wavelength times the frequency. Right? And we're talking about the fundamental frequency here, and so we have that for the fundamental frequency, that'll just be equal to 2 times the length, and so this will be 2 times 1.2, and so this will be 2.4. Okay. So we now have lambda, so we got that number to plug in. The frequency number was given in the problem, and so the wavelength, or the velocity of my wave, will be given by 2.4 times 140. And so we get that this will have a velocity of 336 meters per second. So now we can take this number, and we can take that, and we can plug it into this problem, and we get that the tension in the wire will be given by 336 squared times the mass of the wire, which was 10 grams, and so we need to convert that into kilograms, and so that'll be 0.01. That means grams, and my length of my wire, which was 1.2. Okay. And so we plug that all in, and we should end up somewhere on the order of 800 and somewhere in the order of 850 units for that. Okay. All right. So we know what the tension the wire has to be in order for this to work. Okay. And then I also want to know what is the frequencies of the first 4 harmonics, and so we can go to the second part of this question. And so what are the frequencies of the first 4 harmonics So the first one I gave you in the problem, the first one was 140. And so all I have to do to get the other ones is basically just add 140 each time. So the first one's 140, the second harmonic is 280, the third one is 420, and the fifth would be 560. And so we get in terms of the tension in the wire and my harmonics for this particular string. And with that, that will conclude Chapter 11. Thank you.